Up now is Larry Hastings, who is standing behind me, talking about stepping through CPython, which he told me is got nothing to do with Python, but more about C. Then in the Caspian venue is Hyperion Development Teaching and Promoting Python. And then downstairs is Test-Driven Development by Charles Haynes and Rachel Laycock. Turn your phone off. Then in this venue after that is Simon DeHaan talking about scalable event-driven architecture with Twisted. And in the Caspian, James Saunders, our hybrid programming journey with Python and C++. And then we have T. So I now happily hand over to Larry. Thank you very much.
Thank you. All right. Ladies and gentlemen, this is Stepping Through CPython. My name's Larry Hastings. I'm going to go straight into things. This was originally written as an Extreme talk for PyCon US this year. And one of the goals of Extreme is very little introductory material, so there will be very little, just this slide really. The goal of this talk is to be an architectural sightseeing tour of CPython. I want to make it clear, by the way, that CPython is the implementation of Python that you're all probably using. If you type Python at the command line, or specifically Python 3, because this talk is given in Python 3. Well, let me back up. This talk is about the implementation of Python, which is, we call CPython because it's the version of Python written in C, as opposed to PyPy, which is Python written in Python, or IronPython, which is Python written in C#, or Jython, which is Python written in Java. Those are all about Python, the language. This is about the implementation of that language written in C, called CPython. So, the goal of this talk is to turn you all to potential core developers. This talk is touching on a lot of the subsystems inside of CPython that haven't been talked about before because there was no way to lump them together into talk particularly good. I took this theory of running it under the debugger and stopping at interesting places. So that's the artifice of the talk. We're not actually going to look at very much Python code. So this is about Python, the language, but it's mostly in C. I'm going to be talking about Python 3.3 because I'm a core developer and I forgot that Python 2 exists. As far as stepping, I'm not really stepping. I'm going to be more running through CPython. I'm going to set a breakpoint and run to it. I'm going to have a little bit of GDB on the slides, just as an artifice to give me structure to the talk. So let's start, however, with a very high-level overview of the Python source tree. These are the less interesting directories, in my opinion. Docs are in doc. The Python parser lives in a grammar directory, which is like a custom grammar definition. I'm not sure where that is defined. Platform-specific stuff is in the Mac and PC build directories for Mac and Windows respectively. And then there's a bunch of crap in MISC and tools, various things. Some of it is internals, some of it are tools, some of it, who knows. Python actually, there's a little bit, there's some strong directories where things are supposed to go, but there's a lot of like, oh yeah, that's in the wrong place, that's in the wrong place, that we just don't fix, because it's better to leave it there than to churn the code. The really interesting 5 directories, however, are these 5, include, lib, modules, objects, and Python. Include is all of the externally visible include files. There are some include files that are in other directories, but those are private only. Anything that is visible to the outside world, anything that is part of the public API, must be in the include directory. Lib is where most of the Python library is defined, specifically the subset of the library that's written in Python. Modules is where the remainder of the Python library is defined. That's the bits that are implemented in C. Objects is a list of the internal Python objects that are implemented in C, like tuple, list, int, dict, string, float, and some internal Python objects that Python the interpreter uses, like a frame object. And the Python directory is where the interpreter writ large exists. So that's where the main eval loop and a bunch of the other functions. We're going to be examining the Python directory more than most talks do. So here's we're going to actually run a program under the Python interpreter, and it's deliberately a terribly simple program that doesn't do anything interesting. But the purpose of this program is to touch on a whole bunch of things that are themselves interesting. So this has a couple of imports, it has a function definition, has a nested function call, a class definition, and an instantiation of that object. And we're going to step through this program inside of how it's running inside of the interpreter, but that's going to take us a while to get there. So you're not going to be tested on this. I'm going to bring it back, but we're not going to look at it for a couple of minutes. So let's start. from the command line, I run GDB on Python 3. I set a breakpoint on main, and I run with that program that I just showed you as the command line argument, and we hit the breakpoint almost right away in module/python.c. That's where main is defined. The first line is this argv copy. So I'm going to talk about what main does. Again, it lives in module/python.c. The first thing it does is it makes a couple of copies of argv. I don't remember what the multiple copies are for, but that's what it's doing. It sets the locale, which is the C library locale, and it calls py_main, which is actually where most of the action happens. So I want to assure you, I'm not going to go into this much detail about every single little thing. I wanted to stop in the main.c because this is like literally the first line of Python when it's running is allocating memory, and I want to talk a lot about memory allocation in Python. So let's do that. Memory management, there are two major bodies of function calls and so on and so forth, entry points in Python for memory management. The two families are PyMem and PyObject. Specifically, there are a bunch of functions in the PyObject namespace that deal with memory allocation. I'm going to talk first about PyMem. Now, when I talk about these allocation functions, they always come in sets of three. There's always malloc, realloc, and free. And they all look the same, the way that you're familiar with as a C program. Malloc takes an int, realloc takes a pointer in an int, and free just takes a pointer. So they always come in pairs in sets of three. I'm only going to talk about malloc just to save time. So when I talk about these things, I'm going to say PyMem malloc. You can assume that PyMem realloc and PyMem free also exist. And speaking of malloc, the actual C function malloc, it's kind of recommended that you don't call it. I mean, it's not the end of the world, but the PyMem and PyObject memory allocation things are there for your convenience. There are good reasons why you would want to call them. There are a couple of calls of malloc in the CPython source tree. Nobody does anything about them because they're not hurting anything, but I don't recommend it for new code. So let's talk about PyMem. That's the one that's called from main. It's defined in pymem.h, and the implementation is object/object.c. I don't know why it doesn't merit its own file. I guess there's not very much there. There's a function called pymem_malloc, the capital M, lowercase alloc, and that literally just calls malloc and returns the result. Unless, I'm going to talk about the macro first. There's also a macro. Macros, we have lowercase characters in the macros, which isn't usually the style, but we wanted to prefix it with the subsystem name. So pymem_malloc, all in caps. That also just directly calls malloc. And this isn't that interesting, except for when you turn on something called pymalloc_debug. That's a compile time preprocessor flag. It's automatically turned on by a configure option called pydebug. And what pymalloc debug does is it switches both of these functions to call, or the function and the macro, to call pymem_debug malloc. Py_debug malloc is like a little mini Valgrind that's built into the Python source tree. It's specifically there to assist with finding memory leaks and array bounds overrides. And if you've ever had to debug memory leaks or array bound overrides in Python, you will appreciate why there is a mini Valgrind built in, particularly if you're on Windows where you can't use real Valgrind and Purify is expensive. So that's all I want to talk about memory management for now. We're going to come back to the other subsystem in a little while when we talk about objects. But let's go to our second breakpoint. We're going to break in PyMain, which actually is just the next function call anyway, continue and hit it immediately. So now we're in PyMain. PyMain is defined in module/main.c, and I sort of wanted to draw your attention to this. Main is in python.c, PyMain is in Python, main is in python.c, PyMain is in main.c, and they're both in the modules directory, even though neither of them implements a module. Again, everything is kind of everywhere. PyMain handles command line option processing. It reads the environment variables that affect the runtime of the Python interpreter. It sets up standard I/O, the standard in, standard out, standard error, the way that Python wants it, because you can turn on unbuffered, for instance. It calls a function called PyInitialize, which is going to initialize all of the built-in objects, the built-in types that are implemented in C. And I'll touch on that in a little while. And then it does whatever you actually wanted Python to do. It runs the script, or it runs the module with -m, or it runs the command with -c. So let's hit our next breakpoint in PyObject new, and we hit it almost immediately because we allocate objects a lot. And I'm going to go ahead and clear the breakpoint because otherwise we would be hitting it all the time. This is a function that is called constantly inside of Python. This allocates a new Python object. So let's talk about PyObject. It's defined in object.h, and the implementation of the generic object is in object.c. And I want to make the point that everything in Python interpreter is a PyObject. Everything that you can think of that is a Python object is a PyObject. It's lists, sticks, tuples, sets, integers, floats, users type classes, and again, a lot of internal things like frame objects. These are all type objects. So because all of these things are this type object, the amount of overhead that it inflicts on you had better be pretty small, and it is. This is all that is required in order for something to be a PyObject. These things have to be at the very top of your structure. So the way that you actually do it is you declare a PyObject and give it some name. Base, I think, is the usual name. And that has to be at the very top of your structure. And then you can put anything you want underneath it. And you tell Python how much extra space you need for your thing. And when you allocate a PyObject, it gives you one of these with the extra space that you needed. And you're supposed to fill in this stuff. So let's talk about what these things are. This first line, PyObject underscore head underscore extra, you'll notice there's no semicolon there. This is a preprocessor macro, and under normal conditions, it evaporates and turns into nothing, which is why there's no semicolon, just to sort of save on wasted semicolons, I guess. Under debugging, if you have PyDebug turned on, then this turns on another option called PyTraceRefs. And PyTraceRefs means that this turns into two pointers. They're PyObject star pointers, and they point to next and prev, which means that we now have a doubly linked list of all the objects inside of the interpreter. If you don't have PyTraceRef turned on, which by default it is not, then there is no central repository of all the objects in the Python interpreter. If you wanted to make an exhaustive list of every object that is allocated in Python, you could not, because there is no list. The only time you get it is when you turn on tracerefs. However, if you turn on tracerefs, you have to turn it on for everybody, because it's changing the in-memory representation of a Python object, which is used all over the place. So you would have to recompile every third-party library that was a DLL or a shared library, because it's going to change the in-memory representation of an object. If you don't do that, then you start referring to, like, internally it's going to refer to this thing that really should be there, and you're just going to segfault sooner or later. Probably sooner. The next thing on here is obref count. This is the reference count. It's an S size t, that's a signed size t, which is supposed to be a signed large native integer. And then when this reaches 0, we call it a destructor. And a destructor, among many other things, it's inside of this type object. Every object has a type object pointer. The type object pointer must not be null. It must point to a legal type object. It used to be that you didn't have to register the type object with the interpreter, but it's a good idea. We prefer that you do that. And let's take a look at that type object. The type object is gigantic. But that means that all this stuff is stored in one place as opposed to being stored in every single object, so that's less overhead per object. This has 52 members. And some of these are data, some of them are function pointers. 4 of them are pointers to structures that have more function pointers in them. It used to be that when you wanted to create a type in C for Python, you would take a static one of these, like, a static initialized PyType object that has a bunch of predefined members. You would find the one that was kind of close to the type that you wanted to make, and you would copy and paste it, and then you would hack it up and change the things that you wanted, because most of them are null and most of them you don't care about, and it's really hard to get them all to line up, and so the copy and pasted one would have comments off to the right that said this, so you could know where you were. And it was really annoying. As of Python 3.3, I think, there's something now called the stable ABI, which is from PEP 384, which allows you to define these at runtime using function calls, which is a lot cleaner, because generally you're only sending a half dozen or a dozen of these, and the rest of them are the default, which is nothing or 0 or null, and you don't care about them. And so it's a lot easier to read. I highly recommend for new extension types that you use the stable ABI. So those 4 that I mentioned, they're actually right here, like PyNumber methods, PySequence methods, PyMapping methods. These 4 things correspond to 4 of the protocols. And I'm going to talk about what a protocol is. You're actually probably familiar with the protocols because they're sort of inbuilt in Python. It's very much part of the Python DNA is the protocol. You may not have heard the term specifically. From the C perspective, they're defined include abstract.h, and the implementations such as they exist are in object/abstract.c. These are abstract implementations of interfaces for doing something on a specific type. It's like an abstract base class, but in C. And you're really actually familiar with the protocols because they're standard things in Python. In CPython, there are 5 protocols: object, buffer, number, mapping, and sequence. So if an object behaves like a sequence, then it implements the sequence protocol, which means that it has a non-null TP as sequence member, which is that structure of additional pointers. So that's, I mean, you deal with this all the time from the Python perspective. From the C perspective, this is what it looks like underneath, and it's actually how it works underneath as well. For a list implements TP as sequence, but not mapping. A dict implements both sequence and mapping. And longs and, all we have in Python 3 are ints, which are the old long, and that implements number. There is something internally called fast sequence, by the way. If you're writing C code to iterate over a sequence, it's recommended to use this. What a fast sequence is, it's an extra API in abstract.h that has a little bit of special case code. If we know for certain that an object is a tuple, then we know exactly how to pull the stuff out of it directly. If we know for certain that an object is a list, we know how to pull stuff out of it directly with a slightly different way. If an object implements the sequence protocol but is neither a tuple nor a list, then we have to go the slow way about it, which is to call the functions that are in the TPS sequence thing and construct the list. And what it actually does is, if it's not a tuple or a list literally, then it iterates over it and creates a list so that you have that to iterate over, and then it becomes quick for iteration. And there's some guarantees that fast sequence makes, like it won't call Python code while you're doing the iteration. That may be helpful to you. Anyway, let's talk a little bit about reference counting. As you all have heard, that Python is internally reference counts. All of these objects have the reference count, as you saw. There are a couple of macros to make life easy for you. Incref and decref, obviously increment and decrement the reference count. Xincref and xdecref are safe versions of those. Those inspect and make sure that O is not null before they do any work. So it's legal to pass in a null and that won't hurt anything. And PyClear is a version of xdecref that also sets that object pointer to null. So that does a little bit of nice cleanup for you. And it handles, if it is null already, it's not an error. So now that we're talking about reference counting and allocation, deallocation, it is finally time to return to memory management. This is the second major subsystem for memory management in Python, the PyObject underscore memory allocation functions. These are in object_impl.h and object.obmalloc.c. This is a subsystem. It's what's called a small block allocator. It's for allocating lots of tiny little slices of memory in a very efficient way. The Python small block allocator is only active if this with PyMalloc is active, but it's on by default. You can turn it off if you want things to actually call malloc directly. I think I have a thing about that. If you have PyMalloc debug turned on, it also goes to the mini Valgrind. But if you turn everything off, then you just get everything calling malloc and free, which means that you can use Valgrind or you can use Purify and you can actually see those allocations. Because otherwise, Purify and Valgrind won't have any visibility into the small block allocator because of the crazy way the small block allocator works, which I'm about to show you. So there's the function called PyObjectMalloc, and there's also a preprocessor-defined PyObjectMalloc with all caps. In general, I recommend using the preprocessor defines just so there's a little bit of extra compile time flexibility. And again, if you have PyMalloc debug turned on, it calls into the mini Valgrind. So let's talk about the small block allocator. I'm going to walk you through how the small block allocator works. I'm going to walk you through starting at one end and winding up at the other, based on the structure, like the recursive structure of how these things are built from the top down. The way that they're actually called is the other way around. So I'm not going to actually talk about the function calls and things until I get to the end. But I thought this was the clearest way to talk about it. So we're going to talk about the data structures from the top down, starting with this struct arena object. An arena is basically allocating a big giant blob of memory from the C library and cutting it up into small pieces. That's what arenas are. And the way that Python works, it has this struct arena object, and that has a pointer to the arena itself. The arena is 256K. That's a big chunk of memory if you're 1991. And what Python does with that is it carves it up into 4K blocks. These 4K blocks happen to be 4K aligned. That's going to be important in a minute. And what do we do with these 4K blocks individually? Well, I'm going to sort of zoom in on one. And we carve it up. The first thing that goes into it at the very beginning of the 4K block is something called a struct pool header. After that, we slice it into individual byte-sized pieces of a particular size. The small block allocator handles allocations from 8 bytes up to something like 224 bytes, I think, in 8-byte increments. So 8, 16, 24, 32, etc. Each of those slices are going to be of one size. It'll be 8 bytes or 16 bytes or 24 bytes. And we just carve up as many of those as we can for the remainder of the 4K after the struct block header. We then create a free list and add all of the blocks to it. And then when you allocate memory, we take something off the free list and we hand it to you, and then we allocate the free list forward. You know how free lists work. So the first thing I want to say is that there is no per block allocation. You'll notice that I said if you have a 24-byte allocation pool, then each of these is 24 bytes long. There is no little header on the front saying, yes, I know what state I'm in, I'm allocator, I'm free, or I'm pointing to the next one, whatever I'm doing. There is no overhead. All we do is we say, oh, you want 24 bytes? Here's 24 bytes. And we just hand it to you from the middle of this thing. And at that point, actually, the small block allocator has forgotten that the memory exists. What happens, the really clever part, the reason that, first of all, this is clever because it has no per allocation overhead. When you call free, what it does is it says, so you've given me this pointer. Well, is this one of ours? So what they do is they iterate over the arrays of the arenas, and they say, is the pointer that you just gave me inside of the memory space of that arena? Oh, it is. Okay, great. Then we know exactly what it is, and it's one of ours. You take that pointer address, you chop off the bottom 12 bits to get to you basically zero out the bottom 12 bits, which gives you the address of this struct pool header. And now you know the size of the thing in the pointer to the free list, and you just throw it on the free list and you're done. Which is why double frees are absolutely terrible in CPython. If you double free an object, then CPython has no idea that it was already on the free list and says, oh, okay, great, and then adds it to the free list again. And so it means it's going to be handed out again, which means there are going to be 2 instances of it. It's time for a bus error. So don't double free in Python, and that's why we happen to have a mini Valgrind built into it. So where do these struct pool headers live? The struct pool headers are themselves in a doubly linked circular list, and that doubly linked circular list is linked to from a static structure called static pool p used pools. A pool is that 4K block, and a pool is in one of 3 states. Unallocated, which means that it's on a free list of pools waiting to be used. Used, which means that some of the memory blocks inside of it have been used and some of them are free. And full. I don't remember what full is called, but full means that it's actually completely unlinked from here, which means that we don't have any reference to it. So again, when something is fully in use, Python has no idea that it even exists. It forgets that it exists. It will come back into existence from the perspective of the pool small block allocator once you free one of the things inside, at which point it will be re-added into this used pool list because there is something free in it. But if it's full, it's not interesting. Now this small block allocator, this is why Python processes seem to always grow and never ever shrink. The problem is, if you have one block allocated inside of one pool, inside of one arena, then you can't free that arena. And so what tends to happen is you allocate a whole bunch of stuff, you use a whole bunch of arenas, and then you free some of them, but not all of them, and so all of the arenas have to live. And so Python processes grow and get to a certain size and kind of stay there. There was some effort to mitigate this behavior all the way back in 2.5. It kind of helped a little bit, but not a whole lot. And here we are. There has been no change in it since. It's hard to say what we could do in order to mitigate this behavior. But it's felt to be worthwhile because the small block allocator means that Python memory usage itself is very efficient and very fast, actually. So let's go back to our breakpoints. I'm going to set a breakpoint at pyeval_evalFrameEx. That's a function name I'm going to get tired of saying very soon. We continue, we hit it almost immediately, and I'm going to clear that breakpoint again because we will be hitting it all the time. So what is pyeval_evalFrameEx? This lives in python/ceval.c. This is what I refer to as the big eval loop. This is the beating heart of CPython. This is the bytecode interpreter, if you've heard of bytecodes, and if you haven't, you're about to. This single function is 2,300 lines long. It is the implementation of every single bytecode, all in one giant function. I would describe it as a stack-based virtual machine for Python bytecode. A virtual machine, in this case, is one of those analogies in computer programming that I think is really apt. It is both virtual and a machine. It is virtual in that it doesn't really exist in hardware. It's just a piece of software that helps keep your computer warm. And it is a machine in that it is a computer, and it has all the attributes that a normal computer would have. So for instance, it has registers. These are all the variables that are declared at the top of that 2300 line functions, pi_eval underscore eval frame dx. And you'll notice they all say register. That's kind of an inside joke. In C, the register keyword is almost worthless. But these represent the same sorts of things that a CPU would have. These 5 here, X, V, W, U, and T, are general purpose registers that are free for implementations of bytecodes to use for whatever they like. This stack pointer up here, this is basically equivalent to the instruction pointer. And then there's a frame pointer in here somewhere and all sorts of other nonsense. So our virtual machine has registers. Our virtual machine also has opcodes. The opcodes are defined in include/opcode.h. I think they're hand edited. I thought they were generated by a Python script somewhere. I can't remember anymore. Anyway, there are 103 opcodes right now. Not all of them fit on my slide. I'm going to talk about some specifics. In general, these opcodes behave like machine language instructions. The Python virtual machine is a stack-based virtual machine, so there's a bunch of stack operands like pushing and popping. But there's a lot of branch if zeros and things like that. There are also some custom ones that are really only relevant to an object-oriented programming language like Python. Of course, they're very specific because they are for the use of Python. They're for Python's convenience. So how would you implement one of these virtual machines if you were going to write one in cross-platform C, like Python? The traditional way would be with what's called a switch loop, or that's what I call it. You have a for statement, and you iterate forever or whatever you like. And inside of the for statement, you're switching on the bytecodes. And here we have the traditional C idiom of dereference the pointer and increment. So we're just iterating forward in an array of bytecodes. You switch on that bytecode, and whatever it is, you jump to the implementation of that bytecode. And this code there is going to do whatever it should do. If binary add, it's going to pop the top 2 things off the stack, add them together, and push the result. Now, this is how Python worked for a long time. It literally had a for loop and a switch statement inside. Now it has something slightly more complicated because of an optimization contributed a couple of versions ago called faster opcode dispatch on GCC. This is using, I give you the issue number, it's 4753 on the Python bug tracker. This is using an extension to GCC that's been adopted by a bunch of other C compilers called, it's sort of a pair of things that work in concert, labels as values and computed gotos. So it's supported by GCC, obviously. It's also supported by Clang, by Intel's ICC, by Sun Studio C. The one holdout is Microsoft Visual Studio, as usual. And so CPython actually has both implementations. It can support this form of opcode dispatch, or it can support the big for loop with the switch statement inside. And that's done using some more crazy macro magic. You'll see in a minute. So the basic way that this works, here's an example of code using both features. This first line, void star pointer equals $& label. That $& that is a new operator. That's the labels as values feature. The unary $& means the thing on the right must be a label. A label is a thing that goto goes to. So it's something. It's a keyword followed by a colon. And labels actually technically are both all the way at the left column or whatever you like. The indentation doesn't matter because it's C. Or case statements are actually also labels. So we have this case label here colon. That word label, that's what we're referring to right there. So this $& unary operator takes the address of the code at that label and returns that as a void star pointer. The next line is using the other feature, computed goto. Goto normally just goes to labels, but now we have an expression here. We have star pointer. We are dereferencing a null pointer, which makes me feel a little funny every time I do it. But what this is doing is jumping past this exit and all the way down to this label here. So this code is going to print foo. It is not going to exit. With that feature, you can write an even more efficient bytecode interpreter. By instead of having a big switch statement, you can have the individual implementations of bytecodes jumping to each other. And the reason that's faster is not because switch statements are slow necessarily. It's because modern computers have what is called branch prediction. Branch prediction is stored per goto, per jump, or whatever it is. And the problem is, if you have one giant switch statement and the dispatch at the top that jumps to 100 different opcodes, it can't predict what the next one is going to be based on what the last one was because it just doesn't have enough data. The branch prediction cache is this tiny little thing. So what this does is it spreads out the branch prediction to each opcode, predicting what the next opcode it might jump to is, which allows it to do a much better job. So this was like, I don't know, a 20% speed up or something in Python. It was ridiculous. It was fabulous. So let's talk about bytecode. And finally, we're going to return to our Python code that I talked about. I'm going to walk over every single line of this and show you what the bytecode was that was emitted by the Python compiler, and step through the Python bytecode and tell you what it's doing. So let's start with the first line here, import sys. This turns into 4 bytecodes. Now I want to talk about the structure just a little bit. This bolded number left column by itself, that's the line number. So first of all, this is the output of the dis module, DIS, short for disassembly. So this number here, that first number in the column by itself, that's the line number that came from, because this is line number 1. The second column is the bytecode offset. Bytecodes are 1 byte by default, unless they're 3. If they're 3 bytes, then that's because they take a 2-byte argument. The bytecode by itself is always 1 byte. So this is showing you that the first bytecode operand is at offset 0, and the second one is at offset 3. All of these are taking arguments, so they're all 3 bytes apiece. And by the way, in case you're wondering which ones take arguments and which ones don't, it's very clever. There's like any opcode higher than 90, I think, takes an operand, and any opcode lower than that does not. There's a preprocessor defined that says these and above. So let's talk about what these opcodes are doing. Load const loads a constant from the constant table. The constant table is just a Python list that's associated with the code object. And it just has a bunch of constants in it. The constant can be anything. It can be 0, it can be none, it can be a tuple. It can be any, basically, Python immutable static type, but it can be composed. In this case, what the argument to load const is a 16-bit number, which is an index into this constant table. And this is very helpfully showing you what is at that offset in the constant table. In this case, it's 0. So what this instruction effectively does is it pushes a 0 onto the stack inside of the virtual machine. Next instruction is very similar, except it's pushing offset 1, which is none. So now we have 0 and we have none on the stack. And now we're calling import name. Import name is the import machinery. Its argument is an index into a different table called names, which are all strings. The name at slot 0 is sys. This is import sys. So import name is calling the Python function dunder import. So underscore import underscore underscore. That takes 5 arguments. In order, name, which is sys, we see here. Locals and globals, which the import name opcode always uses the local, the current, locals and globals that are effectively part of the running instance, so it's not passed in. And then the fourth and fifth arguments. The fourth argument is a from list. This is when you use the form of from x import y. That's a list of names, so it's another a Python iterable of strings. We don't have from x import y. We just have import here. So the none represents our from list. And the fifth argument is what's called a level, which indicates whether it's a local, an absolute or a relative import. This is an absolute import, so it's a 0. It's an absolute. It's kind of that number. So what import name does is it imports the module, whatever you've asked for, and it pushes the result on the top of the stack. Now, what's happening inside import name? Well, in this case, not a lot. Let's talk about preloaded modules for a minute. In Python, there are a whole bunch of modules that are already imported before you ever get around to running any of your own code. And you can see a list of them very conveniently. If you just say import sys and then print out sys.modules, this is a list of cached modules inside of the interpreter. And since sys is one of them, then you're not really doing anything by doing that. And so this is literally the list. And as of Python 3.3, there are 54 predefined modules. Most of these are implemented in C. Some of them are implemented in Python, which means that Python has actually been running Python code before it ever got around to running the code you actually wanted. A little scamp. So back to, well, let's talk for a minute about modules in C. I'm not going to talk about it very much. So the ones that are built into the Python interpreter are generally in the modules directory. They're all initialized by this PyInitialize function. It's called from PyMain. And I'm not actually going to spend a lot of time talking about the extension module API because it's something that's been discussed to death by other people. There's a very good documentation built into the Python documentation called Extending and Embedding the Python Interpreter. Talks all about writing extension modules and runtime C types. And there's also a very good talk from a PyCon a couple of years ago, Ned Batchelder's A Whirlwind Excursion through PyConZA extensions. So I will direct you to those there, and not another word will be said. So let's go back to our bytecode. We just talked our way through import name. Import name, it looked in sys.modules, found that the sys thing was already there, and just returns it. Sys.modules, anything you put in there, it'll be looked up by name and handed back to you. So you can put anything you like inside of sys.modules. It's just a dict. If you assign sys.modules brackets foo equals 3, and then you say import foo, it'll be 3. So that's all that imports name does. It hasn't done very much work this time. And boom, now we have store name. Store name, again, is using names array. So it's that same 0 maps to the same string sys. And what it does is it pops the top thing off of the stack and binds it in the local global namespace, the module namespace, to whatever that name is. So we have just bound sys to the return of import name, which is the sys module. Boom, we now have a variable declared called sys in our module scope. So the next line is almost the same, but it's importing a different module called color_sys, and it's exactly the same except for the index into the name array, the name array, which is index 1, which is color_sys. Color_sys I picked almost at random. It kind of wasn't important what it actually does. What color_sys does is it's color space transformations like RGB to HSV or something like that. What's important is that A, it's implemented in Python, and B, it is not preloaded. And the reason I wanted to do that is because I wanted to talk about the import mechanism itself a little bit. So this is the source code for color_sys, but we don't actually use it when we import it because we have a cached version. This is lib pycache color_sys.pyc for Python 3.3. Don't attempt to read this, you'll go blind. But I just wanted to draw your attention to the format of a PYC file. A PYC file, this is a Python object, or actually 3 Python objects that are stored using what's called the Marshall module. Marshall is a runtime serialization and deserialization library. It's used by Python itself, and I don't recommend you use it for your own code because it changes a lot. It is there strictly for the convenience of Python. The only reason that I would use the Marshall module is if I wanted to open up a PYC file and examine it myself. It's implemented in Marshall.h and Marshall.c, of course. So let's talk about the structure of the PYC file. It contains 3 things. The first 2 are integers, and the third one is a code object that represents the module that you want to load. The first integer is this first 4 bytes, OC9E0AOD. The second is a time. So I'm getting ahead of myself. The first one is what's called a magic tag. This is just a magic number that tells Python what version of Python was used to generate this bytecode. This magic tag number, OC9E0AOD, this is the one for Python 3.3. There have been 50 of these tags defined so far, and you may remember there haven't been 50 versions of Python so far. These tags change a lot. They used to change more often. Now they tend to change during alphas and betas. They don't change as of the feature freeze, and they don't start changing until we get to the next alpha at this point. But it did change several times during the development of 3.3. Now, OC and 9E, those are just numbers to represent the version number. It's like a little endian 3230. That's the number is supposed to be like 3.2 at 3 or something. I'm not sure what the number. It may not correspond to anything. I don't think it does. The next part, this ODOA, what happens is that if you catted this PYC file, I'm going to go back a little bit. If you catted this PYC file to the terminal, then what you would see is a line feed, that's that \f, followed by a lowercase z with a little inverted hat on it, and then a character return line feed, so you get a new line. And then it would be followed by garbage, and it would probably reset your terminal, so I'm not sure this really helps anything. But it was a clever idea. It's kind of like the zlib header, I think, or the ping header. So the next 4 bytes are, I went too far. The next 4 bytes are the M time, the modification time of the original .py file that this is representing. This is how it knows whether the cache is up to date or not. If that time does not exactly correspond to the .py file's STM time, then we throw this away and we regenerate it. And again, following those 8 bytes is just a single serialized code object that represents the module. So if you import color_sys, it's going to read this in. Assuming that the M time corresponds and the magic tag is legal, then it's going to take that code object and turn it into a function and call it. And the result of that operation will be the color_sys module. So let's talk about the next line. We have a def foo with the definition of a function here. Load constants and store name I've talked about a bunch of times, so I'm going to stop talking about them. But make function is pretty interesting. So load const, first of all, actually I will talk about it a little. You'll notice that it's indexed 2 into the constant array, and that is a code object. It's not a string or an integer. It's a very complicated object. It's not byte. It's sort of raw bytecode, and we need to turn it into callable bytecode, which is what make function does. So we push the code object on the stack, and then we call make function. The argument to make function is that 16-bit integer. It's actually 3 integers that have been sort of bit shifted and smashed together. The 3 numbers represent how many keyword arguments there are for the function, how many positional arguments. Excuse me. Let me restate that. I made a mistake. How many positional arguments with defaults there are for the function, how many keyword arguments with defaults there are for the function, and how many type annotations there are, because of course Python 3 has annotated types for functions. Since foo doesn't have any of the above, the number is 0. Now I'll point out, we don't actually see the code for foo here. There's no bytecode for multiply, for instance. There's nothing fetching A or B. The code for foo has already been tokenized, and it's living in that code object. I'll come all the way around and show you that in a minute. But I just wanted to point out that it doesn't exist here. So this is what's called function binding time. When you have default values for a function, this is when they're defined. So like if you have A equals empty square bracket, this is when the list is created, and it's passed in and created as part of the function header. And that's why you have a single list that lives for the entire life of the function. And then store name, again, we're binding foo to the result of make function. Make function pushes its result, which is a callable onto the stack, and we're done. Now we have foo. So this is our nested function call. Load name is the corresponding thing for store name. It's indexing into the same array. Print is a function. It's a global function, so it has to look in the built-ins. Foo is defined in the module, so it finds that sooner. And then we're defining, we're loading constants, offsets 3 and 4, which are the numbers 6 and 7, and we're calling call function. Call function, again, that number is a couple of numbers smashed together and bit shifted together. It's telling us how many positional arguments there are and how many name arguments there are. Positional arguments are just pushed on the stack like this. Name value arguments are pushed as pairs of names and their values. Since we don't have any name value things, we don't have any funny high bit thing. It's just the number 2 because there are 2 arguments to foo. The result of call function, it pushes the return value on the top of the stack. So at the end of this call function 2, that's the result of foo. And that output of foo is the input to print, so we just call function directly at that point. We call function 1. Call function actually takes the parameters off, and then it looks for the callable itself, and that's why we pushed those things at the beginning. So it's almost like it's efficient. The result of calling print, print returns none, I think. Every time you have a function in Python, you always return a value. And if you don't care about the value, then we have to get rid of it. So pop top, all that does is it takes the top value off the top of the stack, frees the reference, and drops the stack pointer and moves on with its life. The last thing we do here of any interest, really, is binding a class. Binding a class is very similar to binding a function, but it's just a little bit more involved. So load build class, that's kind of loading the equivalent to, golly, I don't remember what that does. Load build class, look it up for yourself. That's an experiment that's left to the reader. Load const is loading the code object that represents the class. You remember that we could have any code we wanted inside of this class definition. We could call functions. We could assign variables. We could define methods. All of that is executable code, and we actually execute it at this time. So what we're doing here is we call load const, make function, load const, which is the argument C, that's the name of the class, which is passed into the function, which is the code object that defines the function. And then we call that function. So that's the time that when we're running all the code inside of the nested class statement. And the result of that call function is the class object itself, and we store that name. So I think this is a good time to point it out. Store name is the mechanism that we used for binding function calls, for binding classes, for binding imports, and for declaring global variables. I guess we have the global variables on the next screen. This C equals capital C. We're using store name here as well. So the same mechanism is used for any kind of global. Python does not differentiate. There's nothing special about the import statement. There's nothing special about the def statement. It's just binding using the same mechanism, and it just happens to be that it's binding different values. So once again, we're calling C, and C is just like any other callable. At the bytecode level, it does not differentiate between a function and a class. It looks exactly like the function calls did before. So let's return back and talk about the bytecode that's inside of foo. This looks a little bit different from our other stuff because now we have load fast. Load fast and store fast are slightly different from before. Load fast and store fast are indices into a local array of locals. It's a list that's allocated at the time that you jump into a function. And it's much faster than looking things up in a dict or something like that. Python actually uses dicts for symbol tables. But if you know that something is a local variable, then it just goes in this fast local array. I didn't do that. And arguments and locals, locally defined variables, both live as offsets into this locals array. So when you call a function, it assigns the first n arguments, whatever it is, in the fast locals array, and the rest of them are actually assigned to null. In Python internally, in CPython, null represents, I don't know what this function is. Oh boy, I have about 2 minutes left, don't I? Less. Okay, I'm going to go really fast. So load fast is pulling those arguments off, pushing them on the stack, and calling binary multiply. Let's talk about binary multiply really, really quick. So here is the bytecode. This is the implementation of the bytecode for binary multiply. This target, that's the thing that allows us to be switch or go to labels as values. Pop and top, those are popping the top value off the stack and just examining the top value of the stack. Multiply theoretically pops 2 values off and pushes 1 value on, but it's cheaper to actually just pop 1 off and then overwrite this one. That's what it's doing. PyNumber multiply is actually doing the work of multiplication. This is the number protocol. This is what's defined in abstract.h. And the implementation of PyNumber multiply is this. It calls binary op1, which handles it if it's really multiply between numbers. And if it isn't a multiply between numbers, then maybe there's sequences. And so we see if one of them is a sequence or the other one's a sequence. And if that works, then we have the multiplied sequence thing, the star A, quote A star times 3. If that doesn't work, then we return an error. And we actually return null, which indicates an error. And we have thrown an exception. And we return whatever the result is. Back here, we now throw away the references for V and W. And we are certain that they were legitimate references, so this is not X daygraph. We set the top to the result, and if it was null, then it happens to be null. And if it was not null, we call dispatch, which for switch threaded jumps to the bottom, and for go to, it actually goes to the next instruction, unless X is null, in which case we're going to break, and we're going to go down to housekeeping, and we're going to handle returning the result. And now I set my last breakpoint, and I'm executing the function. All right, the result of the program is 42. That's very clever. I'm out of time. Thank you very much.
Thank you very much, Larry. I have time for one question. So you better make it good. No pressure.
Do you ever have a need for more than 64K constants?
Not so far. If there was a need for additional constants, then we would probably have to add new opcodes. But yes, so constants and names are in separate tables. And then local variables are in a third table. There are 3 or 4 of those little tables like that. And yes, it hasn't been a problem so far. Fingers crossed.
Thank you very much, Larry. Appreciate it. I'm sure that you will find people outside wanting to ask you more questions.
I might know the answers to.